weekend or a good week, depending on when you're watching this, especially after the difficult weather, to say the least, that we had these past few days in Austin. So basically how this is gonna go, I'm going to make shorter videos that altogether would amount up to one full class. And the idea is that in that way you can be a bit more flexible on whether you want to watch the whole class altogether or you want to separate and watch each video individually. They are meant to go in a sequence though, so if you start with the first one, just be sure to follow with the following videos in that sense, okay? So now let's get started to what we'll be seeing today, which is randomized controlled trials. So, as you know, last week, the week before that now, we started seeing what potential outcomes were. We studied a little bit about the framework, and we defined what causal effects and estimates were as well. So the idea is that this gives us the foundation to think about causal inference in this sense. Okay, so again, potential outcomes is gonna be a common theme throughout all these different classes, either whether we're seeing experimental strategies or observational studies. And we're gonna be starting with that today. We also looked a little bit into bias in causal inference. We talked about the ignorability assumption, which is the same as the independence assumption or exchangeability assumption. Again, these terms are going to be used interchangeably in this class. We also talked about what confounding and collider bias were. Remember that confounding bias means that there's a variable that is correlated both with the treatment and the outcome and affect both at the same time. And thus, when we try to detect a causal effect, we can't because that variable is confounding, okay, and thus biasing our effect. Collider bias is a different thing, and it's a variable that basically is affected by the treatment and the outcome, okay? It's usually a variable that is measured ex post, so you have to always be aware of that when we're looking on whether to include certain variables or not. Today we're going to be looking at our first identification strategy, which is sort of the simplest to a certain extent. It relies on the least amount of assumptions, and it's oftentimes considered the gold standard for causal inference. So that's why we're going to start with this today. And we're going to also see, of course, the limitations. So we're going to be talking about the assumptions and the power of randomization and design, for that matter. We're going to be talking about what things we should consider when we're actually designing an experiment, because we get a lot of freedom to what to include or not to include in that sense when we're designing a field experiment. And finally, we're going to be talking about the limitations, things that you need to look out for in that sense. So let's start with the magic of randomization, okay? So as we saw the previous class, we had the fundamental problem of causal inference, which is basically that we can only observe one potential outcome at a time, right? So if we have a treatment variable that is binary, 0, 1, the typical example that we kept mentioning the previous class was whether I take an aspirin or not when I have a headache, right? So when we have a binary outcome, then we have two potential outcomes, one for each level of the treatment in that case. And we can only observe either Y0 or Y1. So either I take or not take the pill for each individual. So the fundamental problem of causal inference is that we can never observe both, and thus we can't get an individual causal effect. So here comes the need for the ignorability assumption, which basically means that if the treatment assignment is independent of the potential outcomes, then I can basically rewrite this and obtain an average causal effect for a group, a sample, or a population, okay? Here, in this case, if you see, I'm now using the binary notation for Z. We have seen this for binary outcomes, so Z equals 0 or 1, and I had explicitly written out Y0 or Y1. In this case, I'm just using a lowercase z meaning that Z can take different levels, not necessarily 0 or 1. So this is also related to what was in the previous homework. As you might know, we mentioned and we talked about the fact that treatments do not need to be binary, okay? For the only thing that you should always have in mind is that for every level of the treatment, in that sense, you will have a potential outcome. So if you have a continuous variable for each value of that continuous variable of the treatment, you will have a potential outcome, okay? So in a continuous variable, you have potentially infinite amount of potential outcomes. For a categorical variable of 5 levels, for instance, you will have 5 different potential outcomes, okay? So in this case, this is just the generalization of what potential outcomes are and what specifically is the ignorability assumption in this case. So again, each potential outcome at any level of C needs to be independent of the treatment assignment. The main problem also that we have is that most of the times the ignorability assumption doesn't hold. If you remember, we saw 2 specific types of biases for the average treatment effects. Okay, just take a minute, think about them. If you remember some of the conversations that we had during a previous class. Some of those biases that we saw, we named them selection bias and heterogeneous treatment effect bias. This is for an average treatment effect in this case. Selection bias refers to the fact that even under the control, in the absence of the treatment, both the treatment and the control group would have fared differently, okay? So that means that basically people that opted into the treatment might have been because they knew that they expected that they would have done worse, even in the absence of treatment, compared to the control group, okay? The idea of heterogeneous treatment effect bias is the difference in the return of the treatment. So both of them, now imagine that both of them would have fared exactly the same, both groups, treatment and control group, would have fared exactly the same in the absence of treatment, but the treatment group would have seen a larger effect compared to the control group. So basically they would have taken more advantage of the treatment. That is what the heterogeneous treatment bias, effect bias, basically is saying. So these are 2 types, in this case, of self-selection into treatment, okay? Either because you would think that you would do worse in the absence of treatment, or do you think that you would have taken more advantage of the treatment? So those 2 things, could have potentially biased our estimates for causal effects. And this is basically the problem with self-selection. So in this case, for instance, we have a population where we have, this is a very descriptive sort of scenario. We have different shapes, sizes, and colors. So imagine that each of them are a different characteristic of a population, right? If we have self-selection, then what happens basically is that people select into different treatments depending on their characteristics, and then one of them gets the treatment and one of them gets, one group gets the control. This is not such a big problem if we actually observe these characteristics. So in this case, for instance, I can see that circles are self-selected into treatment, and squares and triangles are self-selected into the control group, right? If I can observe the confounder, then I can control for it. So that is not really a big deal. The problem is when I can't actually observe that variable. If I can't observe a confounder, then I can't control for it, and thus my causal estimates will be biased, okay? When I say observe a characteristic, I mean it's in my data, right? It doesn't really matter that if I look at a person, I can actually see certain characteristics. It needs to be like in my data, and I need to be able to control for it in a statistical sense. So in this case, if the shape is in my data, then maybe I would not have a problem. But because maybe it's not, and it's what we call an unobservable, then this would be a big issue. So the power of a randomization comes from the fact that we can use this to actually make the ignorability assumption hold. So one way that we can do this is actually do it by design. So I have talked a little bit about here about what data generating processes are. A lot of the time we get data, they are generated by sort of a black box that we don't know what it is. And in there you can think about of some sort of machine that has a data generating process that's just spitting out data, right? And most of the time we have no idea what that data generating process is. And that is the biggest problem. If we knew how the data was generated, then we would be able to control for that. And then we wouldn't have such big problems. Here we don't have that issue. And what we can do is actually we can create the random assignment, and we can actually design it in a way that it's not correlated with anything else. Okay, so if I randomly assign a treatment intervention C, then basically what this will buy us is that there will be no systematic selection either on observable or unobservable characteristics. And basically the unobservable part is the one that I'm most concerned about. And this is the very, very big advantage of randomization and randomizing a treatment. That I know that because I designed the experiment and I actually generated this treatment variable, I know the data generating process behind, and I know that it's not correlated to anything else that's out there. So in this case, what we do basically is just randomly divide a population in different groups. If we have a binary variable, then we need to divide it in two groups. So we just randomly separate our group into two and then assign one of those groups into treatment, one of those groups into control. If you had 3 levels of treatment, for instance, you would divide it in 3. When I say different levels of treatment, usually I am including the control group in that. So if I say 3 levels of treatment, it's usually 2 treatment, different treatments, active treatments, and 1 control group, okay? So great. We have 2 groups that I know were selected randomly and were not self-selected in any way. They did not have the power to do so. And basically, I know now that the ignorability assumption will hold because I generated the treatment assignment and it's not correlated to any potential outcomes. So if you remember this picture that we saw the previous class, the main problem with a confounder is that basically it's a variable that affects both the treatment and the outcome, and because this path is generated, then I cannot accurately measure the causal effect between treatment and outcome. With an experimental causal graph, in this case, what we do is that because the treatment was generated randomly, and for the same reason it's not correlated to anything else, then basically I am removing this correlation between the confounder and the treatment, this path here. And if I'm cutting this path, then everything is fine because then there's no confounding. Okay. One important thing to remember is that confounders in the sense of other covariates are still going to affect the outcome. Okay. This path has not been broken. And that is something that's important to understand. For instance, if I randomize access to college for a kid that probably has more money or has their family has higher income, they might do better in some sort of outcome because basically this still that variable will still affect whatever outcome of interest we're looking at. Imagine expected future income. Okay. However, this will affect both the treatment and the control group in the exact same way. So basically will not be confounding my results. They will net out those effects. So that's the reason. There will still be variables that will affect my outcome, but because they're not differentially allocated, if you will, between the treatment and the control group, then everything will be fine in terms of the identification of my causal effect. One important question, however, is to think about whether there are ways that the treatment can be potentially correlated with a confounder. And there's actually two ways that this could potentially be possible. We're gonna look at one of them through an example, but the one that I just wanted to mention first, which is probably the most obvious one, is that it actually can, just by chance. If you think that you have just a lot of confounders, just again, by probability, one of them might be correlated to your treatment assignment. It doesn't say that it was actually generated that way, but again, coincidence happen, and by chance they could be correlated in that sense. So for instance, this is a graph, a plot that shows the number of people who have drowned by falling into a pool, and the films that Nicolas Cage appeared in by year. So as you can see, both of them move very closely together. Okay, this is clearly a spurious correlation. It's very weird that Nicolas Cage would decide to act in more movies when the same year that because more people drowned that year, and at the same time, it would be very weird that because Nicolas Cage appeared in more movies, that people suddenly started drowning in the pool because of it. So again, there's spurious correlations that are going to appear in our data as well, and we need to be aware of that. And we need to be able also to distinguish between what would be something that is just by chance and something that would be more systematic. And then it would maybe indicate that randomization wasn't done properly. Okay? So I mentioned before that RCTs are usually seen as the gold standard or the benchmark for causal estimates, because again, this is very straightforward. You randomize a treatment assignment and then you can very easily just compare two groups. Super straightforward. There's not much fuss into it in terms of statistic manipulation in that sense. And it was actually kind of recognized recently in 2019, if you may have heard or remember, the Nobel Prize in Economics was awarded to Michael Kramer, Esther Duflo, and Abhijit Banerjee. Those three highly recognized professors and researchers are the founders of JPAL, the Poverty Action Lab, which is basically a lab that's based in MIT and has different offices all around the world. And what they do is actually run randomized controlled trials to evaluate different policies. So basically, their whole premise is to bring evidence, hard quantitative evidence, to policy decisions. So the idea again is that instead of just choosing between different policies that you might not be really sure about the effect or whether they work or they don't work, or if you have like a limited budget and you need to choose which one would you actually implement, things like RCTs in this case would be a huge help with this. However, as you might have seen also through Angus Deaton's video, there's not all people are very pro randomized controlled trials. There's a big portion of not only economics but in other fields, basically that they're a bit more skeptical about the usefulness of RCTs, some of the shortcomings that they may come, and moreover, I think just the over-utilization of randomized controlled trials in that sense. And there's some valid points there that we're going to discuss, but just for you to know that usually randomized controlled trials are seen as sort of the benchmark. And if you ever want to estimate a causal effect through other methods, a lot of the times your results are going to get compared to experimental results if they're available. One important thing also to know now that we've kind of talked about the power of randomization and how and everything that randomization can buy us, is how can we actually randomize in practice? Because a lot of the times, if you're designing a field experiment, for instance, you will need to randomize individuals or units into a treatment or a control group. And it's really easy. It's basically a coin flip. And I put a coin flip with an asterisk, basically because a coin flip, of course, has two sides. So you're thinking about binary treatments. If you have more treatment assignments, you can think about a dice, two die, and things like that. But it's just that easy. Of course, in practice, you will never actually be flipping a coin endless times to assign everyone to either treatment or control groups. But the same idea sort of relies behind it. So in practice, in R, what we're going to do actually is use different sampling methods to randomly generate numbers or pick out numbers. And with that, we will allocate certain people or units into a treatment group, certain units into a control group. So let's look at this little snippet of R code that I have here. Okay, so imagine I have 1,000 units, and I generated just a vector of IDs from 1 to 1,000. So that's just to basically identify the different observations. What I first need to do, and this is very important, that's why I'm highlighting it first, you need to set a seed. What that means, basically, is that every time that I run a random function, in this case, so basically when I'm telling R, between these 10 numbers, pick one at random. If I don't set a seed, every time I rerun that command, what's going to happen is that it most likely it's going to pick a different number. Okay? And the problem with that is that you will not be able to replicate your treatment allocation in that sense. And a lot of the times you need to replicate your treatment allocation because you are not going to run this once, but probably you're going to run it a bunch of times. Okay? So you need to set a seed. The number inside the function setSeed doesn't matter, okay? I'm putting 100, you could put 1, you could put any number that you want, an integer number, of course. It doesn't matter. In this case, I just put 100 as any number. You can put whatever. But the thing is, again, I am basically setting the seed in R, and every time I rerun this code, I'm going to get exactly the same result. So that's important. Secondly, what I do is use the function sample. Sample, what it's going to do, it can do different things. In this case, what it's going to do is going to pick 50% of my observations that are in the ID vector. So what I do is give them as a first argument the ID vector, which is basically, again, every unit from 1 to 1,000. And tell R to please, from that vector that has length 1,000, pick up 50% of those. Any random 50%. Sample, again, is a random function. So every time you rerun it, if you haven't set a seed, it will sample different numbers. In this case, the 0.5 is basically saying that I'm sampling 50% of that. And that, I will say that it's my treatment IDs, basically the IDs for people that are in the treatment group. And because I'm thinking of a binary treatment, then everyone that is not in the treatment group, by complement, is going to be in the control group. That is very easy to do. Basically, I say within the ID vector, please select everyone that is not in the treatment ID. Okay? And that's basically what this exclamation point does. It says, do exactly the opposite of what I'm telling you inside this. Okay? Great. This is all also in the R code that I uploaded. So please go in there, run this code, look at the different vectors that are generated, run the different parts of this. So maybe run just this part ID in treat ID, see what it generates. That way you can understand what each part of this code is doing as well. Okay, great. So now I have a vector that it will be treatment ID, and I have a vector that will be control ID. Each of these vectors are gonna be length 500 because I said to this function, please choose 50% of the sample. So 500 are gonna go into treatment, 500 are gonna go into control. Great. Then I need to generate my treatment assignment vector. Basically, again, Z, a vector of zeros and ones. So what I'm gonna do, super easy, is just generate first a vector of just zeros of length 1000. And then I'm gonna say for everyone that's in the treatment ID, just change it to 1. So now basically Z is gonna be 0 for everyone, but for the ones that are in the treatment group and have the treatment ID, it's gonna be 1. Right? So now I generate just a quick data frame, and as you can see, I have 2 columns, ID 1, 2, 3, 4, 5, there to 1000, and the treatment assignment in this case. The first 2 are assigned to treatment, the third one is assigned to control, and so forth. So great, there we have one realization of the randomization assignment. What happens, however, if we need to randomize for more treatments? So now you're not only thinking of a binary treatment, but you're thinking of having, for instance, 2 more treatments, right? So you have 2 treatments and a control group. So now you need to divide your sample into 3. How would you do that in R? One way to do it, if you think about this, is, again, the same way. You have the same IDs. We set a seed of 1000, and we write the types of treatment. So 0 is going to be the control group, 1 would be treatment 1, 2 will be treatment 2. Okay? And now what I'm saying to R is, please take the types of treatment, so 0, 1, 2, and give me a vector of length 1000, okay? I need to say replace true because I'm asking R to give me more, a vector that is longer than the types of treatment that I am providing. Okay, so basically it needs to pick up 0, 1, 2, and then 1, and then 2, and then 0, and it's gonna go like that basically randomly, and everyone is gonna have the same probability of 1/3, 1/3, and 1/3. Okay, so every probability, every group is equally likely to happen. Okay, so as you can see, basically what it does, again, is just goes in and draws this balls, and it does this 1000 times until you get an allocation of treatment assignments. The problem with this basically is that you don't get groups that will be exactly the same size. In expectations, if you repeated this same thing a million times, 1 billion times, you would get groups that are the same size. But again, because of sampling variability, you will not get exactly the same size. Does it matter that much? You gain a little power, as we're gonna see, when you have equal size groups, but this is quite good as well. You're still randomly picking out treatments and treatment assignments, so that's great. It's not correlated to anything, and you have roughly the same size between the 3 different groups. Okay, and again, all of them are equally likely, so all is good. If you really wanted to force this to be exactly the same size, to have 3 groups that are exactly the same size, then what you could do is basically generate a random number that is of length 1000. So basically this, what it's doing is giving me 1000 different numbers that are generated randomly. That is why it has an R here, from a uniform distribution from 0 to 1. So again, imagine a uniform distribution that goes from 0 to 1. It's a continuous number, and I'm telling R, please randomly just choose 1000 numbers from that distribution. it doesn't really matter what the number is. It doesn't really matter what the distribution is either, okay? Just in case. And then what I'm telling R is now reorder my IDs, like reshuffle them, according to the random number that I just generated, okay? So from lower to higher. That number is random, so basically now the order of the IDs is going to be random. So that's basically the strategy here. Sorry. And then what we're just doing is like, okay, this is already randomly ordered. So we know that there's absolutely no pattern there. And we're just saying now, please just assign either 0, 1, or 2. So it will go 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, from 1 until 1,000. 1,000 is not perfectly divisible by 3. So basically, this will mean that the first group will have 1 observation more than the other 2, but they're almost equally sized, okay? So again, I reorder the IDs randomly. So basically, I sorted them in a random order, and then I am allocating the treatment sequentially, 0, 1, 2, 0, 1, 2, 0, 1, 2. And this is what the rep function does. It repeats this vector 1,000 times divided by 3. Plus 1 in this case, because again, 1,000 is not exactly divisible by 3. But that is basically the idea. And again, both this codes work perfectly fine. This is also in the R code that I provided. Please go there and try to do the same thing, but instead with 3 treatment assignments, edit it to be 5 treatment assignments. What would you get there? What would be the event? And see basically how both assignments compare. Okay. One important thing now is basically how do we check that randomization was done correctly? In this case, the easiest way is actually to check for balance. So again, the idea here is to basically see whether the different covariates that I have are balanced between the treatment and the control group. So we're going to use this package that we've used before, which is design match. It has a very handy little function that's called mean tab that it's great to assess balance. And we're gonna read just this data that is covariates example. Okay, this is just randomly generated data. It's also generated in the in the R code, so you can also see it there. But in this case, we're just loading it directly. Okay, and this is basically how it looks. Again, we have our ID, we have our treatment assignment variable, and we have 20 different covariates. Okay, it doesn't matter what they mean. Just know that they are covariates. Okay. And I will need to select just the covariates because again, when I am checking for balance, I just need to have my covariates separated from the rest of my data frame. So in this case, because they're just named x1, x2, x3, x4, the names are super easy and are basically that, x1, x2, a vector of x1, x2, x3, x4. And that is an easy way to write. Great. So then with the mean tab function, the first argument that it has here is basically the matrix of covariates. So that's why from the data frame that I have, I only select the covariates. This is what this is doing, okay? They all need to be numeric as well. So be careful with that. If you don't have a numeric covariate, this function is not going to work. Basically because it doesn't know how to calculate things with non-numerical variables. The second argument I need to pass to this function is the treatment assignment vector. In this case, it's C, right? And then the final two is the indices for the treatment group and for the control group. Basically, the indices, where Z equals to 1 and if I use the function which, that is what it returns. And where z equals 0, and again I use the function which, and that will return the indices. So basically this returns a matrix where each row is a different covariate. So as you can see here, it goes from x1 to x20. And what we really should be looking at is this mean treatment covariate, mean control covariate, which basically tells us what the average is for this covariate in the treatment group and for this covariate in the control group. It also gives us the standardized difference, which means that this is the difference between the treatment and the control group in standard deviations. So again, all of these are comparable between each other, even though the covariates might be in different scales. And basically the function does that behind the scenes. And this is the p-value, which basically tells us whether this difference is statistically significant or not at conventional levels. So if we think that usually conventional levels means lower than 10%, then we can see that there's actually two covariates, x1 and x6, that have a p-value that is lower than 10%, which means basically that this difference is statistically significant at a 10% level, which again is a measure of unbalance. So as you can see clearly, the treatment group has a higher average of x1 than the control group, and the same with x6. So the thing that we need to, the question that we need to ask ourselves here is, did the randomization work? And if the randomization worked, why are there significant differences? So basically the answer here goes back to that idea of correlation just by chance. So in this case, the randomization did work. I mean, and I know it worked because basically I designed all of this, including the data. But there are significant differences just by chance. Again, we have 20 covariates. Just by chance, one of them will be significant at a 5% level, and two of them will be significant at a 10% level. Okay, again, if you take out the 10% of 20, you will get 2. If you take out the 5% of 20, you will get 1. So just by chance, just by random chance, you will get 1 probably that is significant at the 5% level, and 2 that are significant at the 10% level. We did not get more, so that is great. That means probably that our randomization worked and it's fine. And if we had gotten more, then we should be worried, because then that moves away from the just by chance scenario and probably goes to the idea of like, oh, maybe I did something wrong while I was randomizing. Okay, so just be careful about that. The other thing is that randomization usually works, not usually, randomization actually works and balances everything perfectly in expectation, okay? So again, randomization doesn't necessarily assure you balance or exact balance for each sample. So as you can see, none of these differences, well, some of them, but they're not exact zeros, right? There are differences in a lot of covariates, right? Because basically I cannot assure a balance for a specific sample, but it assures balance in expectation. So basically what it's saying, if I randomize a bunch of times and allocate the treatment in different ways, infinite times, basically that will converge into a zero difference, okay? So let's go to R and see how this is done. Okay, great. So the idea here basically is to talk a little bit about this idea of a balance in expectation, okay? So all of this is included in the code that is uploaded with this class, so you can go and replicate it. But a lot of you have mentioned that it is a bit hard, and I totally understand, to follow when I write the code on the slides and then to know basically what to look for. So the idea behind that is basically for you to have the R script that I upload and also have, like as a companion piece, the slides. So the idea is that you can run your own code, but at the same time also see what I get. So the idea for the class slides, including some code, is for you to have that as a backup, but not necessarily for you to be paying super close attention to those snippets of code. You should recognize the functions and things like that, but don't think that just by looking at something that you will know how to necessarily code it. Unfortunately, coding is one of those things that you can only learn by doing. Okay, so I will highly suggest that after this, please go download the R script and start playing with it. Okay, I've made a point to actually include a little bit more questions and kind of like small exercises for you to play around with the data a bit more. So be sure to also do those. And if you have any questions, just feel free to reach out. Okay, so going back to the code. So we're live coding now. Exciting. So in this case, what we want to do basically is talk about this idea of balancing expectations. So I'm going to simulate a bunch of different treatment allocations. So for that, basically, I'm going to set a variable that's called sim, and let's be consistent and do the treatment assignment and do the assignment mark there. I'm going to say that we're just going to run 100 simulations for this. 100 is kind of low for simulations, but again, this is just to show you how this works. Actually, let's put 1,000, okay? Just for you to know. Great. So I put 1,000 simulations, and basically what I want to do is for each different allocation of the treatment that I'm going to be doing, what I want to do is store the difference. For instance, for one covariate, we're going to do x1 in this case because that one was the one that was unbalanced at the 10% level, if you remember. So we're going to store the difference between the treatment and the control group for different assignments for that specific variable, okay? So I'm going to create the variable diff, which is going to be just an empty vector, okay? Just NAs of a length, in this case, the same number of simulations, because each simulation is going to have a difference in between the treatment and the control group, in this case, okay? So I've already loaded the data. So in this case, it's just called data in my case. So as you can see, let me just bring this up a little bit. As you can see, I have the treatment assignment, the IDs, and the 20 different covariates. Okay, so data is the data frame that I'm going to be using in this case. Great, awesome. So now, in order to run this for 1,000 times, what I'm gonna do is run a for loop. Actually, let me put 2,000 just so no one gets confused between the length of the ID and the number of simulations, okay? So I'm gonna say for each S, for S that goes between 1 and the number of simulations, do this thing that I'm gonna put between the curly braces, okay? For 1, 2, 3, 4, until 2,000 in this case, okay? So what I'm gonna do is set a seed, again, always set a seed when you're doing this for replicability. The seed is gonna be changing, so basically what's changing here is S. S, again, starts with 1, then goes to 2, then goes to 3, up to 2,000. So I'm gonna set a seed S, so in each iteration, basically this is changing. If I just set the same seed every time that I randomly generate an allocation, it's going to be the same. Okay, so we don't want that, so we set the seed to S. Great. And then what I need to do is basically do the same thing that we did before, generate the treatment allocation. So I say treat ID will be sample. In this case, I already have the my vector ID that I created before. And I want to take 50% of this, the same as before. Great. So again, this is what we already saw. I give it the number from 1 to 1,000 and tell to randomly pick 50% of these. And by complement control ID, will be every ID that is not in treat ID. Great. And then I'm going to generate the number m, which it's going to be the mean of the data x1 for the treatment group minus the mean of x1 for the control group. Okay, so remember that in each iteration, this is going to change, right? So for 1, it's going to generate 1 allocation of the treatment, and it's going to calculate m. Then for s equals 2, it's going to generate another allocation of the treatment, and m is going to be something different, okay? But I want to store each value of m, so then I'm going to tell this that in the element s of that empty vector diff that I created, please store m. Okay, great. So for you to see how this works, let's assume that s equals 1, and let's run this. Great. So m, it's minus 0.06. Great. What if s equals 2 now? M is 0.05. Okay. So basically, again, this is going to be automatically doing what I was manually doing now. So it's going to go from 1, 2, 3, 4, 5. And every time it's going to store the m on the s position of the diff. Okay. So let's do this. Let's run this whole thing. It takes 1 second. Great. Let's see how diff looks like. And as you can see, each of these is basically the difference between the treatment and the control group for a specific allocation of the treatment. None of these allocations are the same as the other, okay? All these differences are quite small, but again, they're not 0. They're sampling variability in this case. So, but in expectation, as I told you, this should be 0. So if we look at the density function of these differences, they should be centered around 0. So let's plot that. So what we want to do basically is plot the density function of that difference, of that diff vector in this case. That diff is a vector. ggplot actually takes data frames. So we first need to transform it to a data frame. So we're going to say that we're going to generate a data frame that just has 1 column, which is called diff. Great. And then I'm going to go to ggplot. The data is the data that I just passed. So basically this point means that take this and use this as the data. You can also be more explicit and say data equal point. Same thing. And I only have one x, which is diff in this case. And we want the density. We don't really need anything else, but because I like things to look a little bit pretty, I'm gonna do it with a dark orange. I'm gonna set a line width of 1.2 just for it to be a little bit thicker. And I also want to be sure whether this is centered or not at 0. So I'm gonna also do a vertical line. And this is super easy in ggplot, just beeline. And in the aesthetic options, you just put x-intercept, which is basically where it intercepts in the x-axis, and this will be 0. I'm gonna put the color is gonna be dark gray, and the line type is gonna be dashed, which is 2 in this case. Okay, and then I hate the gray background, so I'm gonna set the theme to black and white, so you have a white background. Great, let's see if this works. Let's run it. Awesome. So as you can see here, let me see if I can zoom. I don't know if you're actually watching this. I think not. It's fine. But as you can see here, we have this density function of the difference. It's not perfectly centered around 0, but it's very close to 0. As you can see, of course, it's a normal distribution. That's not surprising. But basically what this means is that even though in expectation, if I take the expectation of difference, it will be 0. So for instance, if I do mean diff, it goes very close to 0, right? There's still certain realizations of the treatment assignment. For instance, like this one, I don't know which simulation is this, but one simulation, for instance, that will generate kind of a large imbalance between the two variables. Okay. This is actually also, the difference is also measured in standard deviations in this case, basically because the x1 is measured in standard deviations. So as you can see, even though most of this is contained under 0.1 standard deviations, there's some that are quite large here, okay, are over that. So again, even though in expectation this is 0, doesn't necessarily mean that every realization that I have is going to be 0. And that sampling variability might generate those imbalances, okay? We just need to be careful and learn how to distinguish that randomness, basically, from systematic differences that might be due to the fact that we're not doing randomization correctly, okay? In this case, randomization is done correctly. There's absolutely no problem with this. So this looks great. So let's go back to our slides. Great. Let me just go back to the slides. Awesome. Okay. So if we just run 100 simulations, I showed you 2,000 in this case, but if we just run 100 simulations, this is what we get. As you can see, this doesn't look that normal. There's kind of like a little bit of a bimodal kind of thing. That's like a little lump there. Okay, this is basically because we don't have enough observations, and this it's a bit bumpy, but because basically because this number of simulations is small. Okay, this has nothing to do with the sample size. Okay, and this is important. There's two different things moving here. Okay, the sample size is always fixed. I always have a sample size of 1,000. Okay, what's changing is the number of simulations that I'm doing. Basically, the number of random allocations of the treatment that I'm estimating in this case. Okay, so as you can see here, this looks very kind of bumpy. It doesn't look great to that side. But if we increase actually the number of simulations, this is 1,000, it already looks a little bit more normal. And if we go up to 100K, you can see that this looks very smooth. And it's also beyond smooth. It goes also like tightening a little bit around the true value. Okay. So that means that when we increase the number of simulations, these extreme numbers are also less likely. So this is the idea that randomization generates balance in expectation, but not necessarily with the sample at hand. So there might be certain imbalances that we have just because of randomness. The idea, the question now is basically, does this generate a problem? And how can we fix it if it does generate a problem? So the main problem here is that we can't ensure balance, as I mentioned before, especially in all covariates. But what we can do actually to minimize certain risks of imbalances that might bias our results is use a stratification process. So we can stratify. What does that mean? Stratification basically means that we will divide our data into different stratums or stratas. Into different stratas or different groups, okay? S, number of groups. And they will be based on one or more covariates. So you can think that you can divide people by gender, or by gender and ethnicity, or I don't know, by gender, ethnicity, and height. Any kind of subgroup that you do, that's absolutely fine. It depends on your design and what you really want to balance on. But the idea is that you generate this groups of kind of homogeneous people, or more homogeneous than the sample itself. And then you randomize in the same way that what you would do in an experiment, but within strata. Okay. So in a typical field experiment, you have just a group of study participants. Okay, so here we have just random people thrown together, and we just randomize, right? And the same way we saw, flip a coin, and you randomize some into treatment, some into control group. So as you can see here, the main problem is that in this group, in the treatment group, just by chance, we got 4 men and 1 woman, and here we got 3 women and 1 man, okay? If we're thinking that there's heterogeneous effects between men and women or something like that, and these imbalances might actually bias our estimates. Not purposefully, in the sense that, again, I randomize, but again, that doesn't mean that because I randomize everything by magic, it's just going to be balanced. Just because, again, by chance, there could be imbalances. If I think that gender, for instance, it's an important variable to be balanced on, then what I can do is actually stratify. So what I do first is that I take my study participants and I stratify in whatever group I think it's important. In this case, gender. So I separate females here and males down there. And then within each strata, I randomize half of them into treatment, half of them into control, and the same for the other strata. Yeah. Sorry. Strata is the plural, stratum is the singular. So basically, as you can see now, there's absolutely no way that the treatment and the control group within each strata are not balanced by gender, basically because they're all females here and they're all males here. But now if I put together my treatment and my control group, you can see that is, by construction, perfectly balanced on gender. So I get 2 women, 2 men, 2 women, 2 men. Okay? Of course, we can't usually stratify on everything, because when you start disaggregating into very small groups, sometimes those groups don't end up with enough people. So you can get groups that have just 1 person or 3 person or something like that, and then you can, if you want to allocate 50-50, then that generates a problem. But basically the limit of this, it's sometimes when you think about matching. So we're gonna look at matching on the next class, but it's an interesting idea here in the limit of stratification. So instead of dividing it into very big groups, you can think that you can actually match your study participants to one other person, one other individual, one other unit that looks very similar to them in other characteristics. And just instead of generating groups of a lot of people, just generate pairs, okay? And with pairs, then basically what you do is for each pair, you flip a coin, assign 1 to treatment, 1 to control group. So by construction, you will have a lot of the covariates already balanced. But again, the assignment will be random, because within each of those pairs, you're basically randomly choose which of the 2 get assigned into treatment or get assigned into control. Again, this is not only for binary treatments. Okay, you can think about doing group of 3s, right? And assigning 2 treatments and 1 control in that group of 3s.